All right, so now we're on Unit 5, and we're going to start off by looking at kind of common graphs, basically, and the end behavior of graphs. So for example, if you have something like x to some even power, that's not 0. So let's say if I have x to the second power, it's going to look like some sort of parabola. All right, and basically as x approaches, notice how as x approaches infinity, our y value, f of x, also approaches infinity. And notice how as our x value approaches negative infinity, so notice how as our x value approaches negative infinity, our y value approaches infinity. And for this graph right over here, if I have, let's say, if this is the graph of y is equal to negative x to the second power, so negative x is some even power, right? Then it's just going to be this right over here, but it's going to be like flipped. So it's going to be reflected about the y-axis. So, if I have x squared right over here, flip it around, put a negative sign in the front. As x approaches infinity, our y value goes to negative infinity. As x approaches negative infinity, our y value approaches negative infinity. Now, let's say if I have x to some odd power. Well, as our x value approaches infinity, our y value is also going to approach infinity. And as x approaches negative infinity, our y value approaches negative infinity for x for an odd function. And you can see that for the example. Let's say if I have y is equal to x to the third power. As our x value approaches infinity, our y value also approaches infinity, right? And as our x value approaches negative infinity, right? X value approaches negative infinity, y value also approaches negative infinity. And if you put a negative sign in front of the odd function, it just flips it around. So if you put a negative sign in front of the function, it just flips it around. So then the trend would be kind of the opposite I said before. As x approaches infinity, now our y value approaches negative infinity, and x approaches negative infinity, y value approaches infinity. So you just have to memorize these couple of rules, and you could just visualize it by looking at the parent functions, or just like y is equal to x to the third power, y is equal to negative x to the third power, right? And then you'll remember these trends, right, just by looking at it visually. Now let's talk about something called the multiplicity of functions. So right over here, I have the graph of y is equal to x minus 3 times x minus 3, or let's write it as x minus 3 to the second power. All right, let's rewrite it like this. And then I have times x plus 2 to the first power. Now, notice how, right, if I have x minus 3 to the second power, then at x is equal to 3, our y value is equal to 0. So basically, at x is equal to 3, our y value is equal to 0. So notice how on the graph, right, we have 3, 0. That's going to be 0 of the function, or a root of this function, right? And notice how if I plug in negative 2 in for x, I get negative 2 plus 2, which is just 0, and 0 times whatever this is also 0. So at x is equal to negative 2, I'm going to have a root there. Now, the main thing to know, there's two things you gotta know. So if you got an even exponent, it's not going to cross. It doesn't cross the x-axis. And if you have an odd exponent, it does cross the x-axis. I'll explain what this means in a second. So look, in this case, I have y is equal to, so far I have this x minus 3 to the second power. And from this rule, we see that if you have an even exponent, it does not cross the x-axis. So notice how at x is equal to 3, right over here, we don't cross the x-axis, right? We kind of dip below to y is equal to 0, right? So we go to the 0, and then we just go all the way back up. We don't cross this x-axis. However, if you have an odd exponent like x plus 2 to the second power, right, we're taking y is equal to x minus 3 to the second power, and we're multiplying it by x plus 2 to the first power. And notice how this exponent is odd. meaning that at x is equal to -2, or basically the root for this part of the equation, we'll notice how it does cross the x-axis. It does cross the x-axis. So in this case, if your exponent is odd, it does cross the x-axis. So that's basically the two important rules you got to know. Now we can actually apply it to this problem right over here, which graph represents the graph of f of x equals x plus a squared times x minus b, where a and b are both positive real numbers. So look, if a and b are positive real numbers, let's just say if, I don't know, I have x plus 3 squared, right? And I have, this is going to be multiplied by x minus 3. So I'm just making numbers up. All right, so let's say if I have this function right over here. Well, where are my roots going to be located? I'm going to have a root at x is equal to -3 and a root at x is equal to +3, right? And it's kind of like the same process we did here. If I have x minus 3 squared, I'm going to have a root at x is equal to 3. If I have x plus 2 to the first power, this is going to be multiplied by x plus 2 to the first power, I'm going to have a root at -2. So the first step to doing this problem is just finding out where the roots are located. So you know, from this f of x graph, I'm going to have a root at x is equal to -3. So at x is equal to -3, I have a root or a 0, and at x is equal to +3, I have a root there, because if I plug in +3 into x minus 3, I just get 0, and 0 times whatever this is 0. All right. Now notice how, all right, so x plus 3 corresponds with this root, right? X plus 3 corresponds with this root, because if you plug in -3 into this part of our equation, we get 0. And notice how x minus 3 corresponds to this root, because if we plug in 3 into this part of the equation, we're going to get 0, okay? Now what we're going to do is basically we're going to find the highest x power. So look, I have an x plus a to the second power. So there's two x's here, right? I have two x's here. And I also have an x minus b. So I also have an x minus b. So that means that I have 3 x's in total, right? And if I multiply them all together, I'm going to get x to the third power. And basically what this means is that my function is going to look very similar to a cubic function. So recall that y equals x to the third power. It looks something like this, where you start out from -infinity and then you go towards positive infinity, right? So basically you count the amount of x's there are, and based on what I said before, like if you have x to the even power or x to the odd power, well, you can kind of predict how the graph would kind of look like. Okay, so I know that from this problem right over here, I'm going to start out from -infinity. So I'm going to start out from -infinity, and I'm going to hit this 0 right over here. Now, because I have an x plus 3 to the second power, well, we said how if you have something for an even exponent, it's not going to cross the x-axis. So this is what it's going to look like. It's going to hit this 0, and it's going to go back down because it does not cross the x-axis. Now, notice how I have a x minus 3 to the first power. And when you have an odd exponent, that means it does cross the x-axis. So notice here, what I'm going to do is I'm basically going to draw a curve here, and I'm going to go up where it does cross the x-axis, right? And this is going to be the sketch for my function. Notice how this looks very similar to a cubic function, right? So, that's kind of like a double check. So, if I know that I have x to the third power, I know my function is going to look something like this. So it wouldn't make sense that my function would look something like a parabola. Okay, so that's kind of like a quick way to check your work. Now let's see if any answer choices look something like this. And whoa, answer choice number 1 looks like this. And that's going to be our answer, right? It hits basically the -0, right? It hits this x plus a part at the root -a, right? And then because it's to the second power, it's gonna kind of look like a mini parabola, right? It just touches the 0, goes back down, and at x minus b, or aka at this root b right over here, what's going to happen is that it's going to cross the x-axis. So then, it's going to go all the way up. That's going to be our answer. Sketch a graph of polynomial p of x given the criteria below. P of x has zeros at -5, 1, and 4. And let me see. So as x approaches infinity, P of x approaches negative infinity. So as x approaches infinity, P of x approaches negative infinity. And as x approaches negative infinity, P of x approaches negative infinity. Okay. So how do we do this problem? Well, first of all, I want to take a look at this end behavior. So as x approaches infinity, P of x approaches negative infinity. As x approaches negative infinity, P of x approaches negative infinity. This looks like some sort of parabola, some sort of negative parabola. And that means that the function looks something like, for example, negative x to some even power. Okay, so that's basically kind of one thing I immediately notice is that I'm dealing with a function that's negative x to some even power, because that's a negative, or that's an upside down parabola, right? Now there's sort of two ways to do this. One way is, well, so this isn't going to be perfect because, I'm doing this on Sketchpad, but basically there's already kind of a graphing error, so ignore that. But basically one way is you can go up, right? So first of all, it kind of has odd behavior, meaning that it crosses the x-axis. So it has odd behavior, basically, an odd function sort of behavior. Then we can hit the 1, go up, and then go all the way down again, and then that should lead us. I think this should be correct, right? Yeah. So this right over here is even, and then this right over here is odd behavior again. Or another way to do this, pretty sure another way to do this is if let's say you have -5, 1, 4. So it's going to be at negative infinity. And make sure to draw arrows, by the way, because remember it's a polynomial, so like it's going to kind of continue on forever. So yeah, make sure to draw the arrows, but it can cross basically at x is equal to -5, and then it can go down below below 1, then it can go down again. So notice here it has odd behavior, meaning it crosses the x-axis at x is equal to 1. It also has odd behavior, meaning it crosses the x-axis. And at x is equal to 4, it has even behavior, meaning that it does not cross the x-axis. And we are done. Kind of just some simple transformations for functions. So I'm actually going to do this pretty quickly. So let's say if I have y is equal to x squared. If I add 3 to this function, it's going to move it 3 up. If I subtract 3, it's going to move it 3 down. All right. So if you add some number c to it, well, it's going to move the function up by c units. And likewise, if it's minus c, then it's going to move it down. It's going to move it down by c units, right? Now, if I have something like x minus 3 quantity squared, it's going to move it 3 units to the right. Okay, so if I subtract 3 on the inside of this function, I move it 3 to the right. And if I add 3 to the inside of the function, I'm going to move it to the left. All right. So that's basically, this should look pretty familiar to you from, algebra class. And also remember that if I put a negative sign in the front of it, it just flips it, basically reflects it about the x-axis. All right, so flips it over the x-axis. Now, if I have y is equal to 2 to the x, if I put a negative sign to the front of it, likewise, right, it flips it about the x-axis. If I add 3 to it, it moves it up 3 units. If I subtract 3, it moves it down 3 units. And likewise, if I subtract 3 on the inside, it's going to move it 3 to the right. And if I add 3 to the inside, it's going to move it 3 to the left. So it does look very similar to, the function transformation for y is equal to x squared. However, there's only one key difference. Is the one other transformation you have to know is that if you place a negative, here, it's going to flip it around the y-axis. Let me just show you an instant replay of that. Put a negative in this, basically next to this x, it's going to flip it across the y-axis. Now, a lot of people get this confused when you're graphing this, y is equal to negative 2 to the x. This is different from y to the negative x power. I mean, y is equal to 2 to the negative x power. All right, so don't get this confused. If you have y to the y is equal to 2 to the x power, put a negative sign on basically kind of the outside, it flips it about the y-axis. And basically the reason why it does this is because for any value of x that you put in, basically you're just multiplying 2 to the x by -1. So all the y values are going to be negative now, right? And so this is going to flip it around the y-axis. However, if you have y, let's say this is y equals 2 to the x, and you place a negative sign here, well, basically if you plug in -1 in for x, imagine if you plug in -1 in for x, that's going to be the same as if you plugged in for the regular graph, y is equal to 2 to x, it's going to be the same as if you plugged in +1, right? And you're going to get the same answer. So every time you plug in a negative value, well, this negative on the outside is going to negate it so that you end up with kind of the positive answer, but it's on the negative x side. This is just another quick question. Which function has the characteristics as x approaches negative infinity, f of x approaches negative infinity? So we'll basically want to find out a function that basically looks something, has an end behavior like this, where as x approaches negative infinity, our y value also approaches negative infinity. So just from looking at these two answers, it can't be one or two, because as x approaches negative infinity, their y values approach infinity, but that's not what the question is asking us, right? We want the y value to be approaching negative infinity. Let's take a look at number 3. So number 3, notice how it has a negative x here. So reminder that when you have y is equal to 2 to the x power, the graph of this is going to look something like this, right? It's kind of what we saw before. Now, if I have y is equal to 2 to the negative x, remember what that does? That basically just flips it around like so. And notice how as x approaches negative infinity, our y value still approaches infinity. So it can't be number 3. And therefore, number 4 is our answer. Now this is logarithms, and I'm going to do a review on that. But logarithms are basically the inverse of exponentiation. And the transformations for logarithms are basically the same, but for answer is, imagine if you have y is equal to log of x, the graph is going to look something like this. Now, what does this negative sign in the outside do? When the negative sign is on the outside, remember, it flips it about the x-axis. So now the function is going to look something like this, where this is the graph of y is equal to negative log of x. Now, what does this negative on the inside do? Well, remember, when you have negative on the inside, what that does is it flips it about the y-axis this time. So negative on the outside reflects it about the x-axis, but negative on the inside reflects it about the y-axis. So now the graph looks something like this, where notice how as x approaches negative infinity, as our x value decreases, our y value also approaches negative infinity. If I drew this out more and more, it's going to decrease and decrease. So yeah, that's why number 4 is our answer. I don't think even inode functions are on the Algebra 2 regions. It's still taught in Algebra 2, so I'm going to teach it, but I don't think the regions really has that many problems on it. I haven't really seen it, but let's just kind of review it. So remember that if f of negative x is equal to f of x, it's even, and if f of negative x is equal to negative f of x, then it's odd. So, for example, an example of an even function would be y is equal to x squared. All right. Or let's rewrite it like this. F of x is equal to x squared. Because imagine that if I plug in f of negative x into my function. So reminder that f of x, right, you're going to have this x right over here. And if you were trying to find out f of 1, well, everywhere you see x, you replace it with a 1. So it's just going to be 1 squared, right? So if I have f of negative x, well, everywhere I see x, I'll just replace it with a negative x. And negative x squared is equal to just x squared because, this negative, you have a negative sign and it's squared. So 2 negatives make a positive, right? And notice how f of negative x gives you the same function as you had originally. In other words, f of x is equal to f of negative x, meaning that our function is even. And basically what that looks like on a graph, if you were to graph an even function, they would be symmetrical about the y-axis. Because if you plug in f of negative x, so you plug in a negative x value, let's say if you plug in a -2 into the function, you're going to get 4, right? And it's going to be the same value as if you plugged in +2, right? If you plug in +2 into the function, you get 4. So it's going to be symmetrical about the y-axis, because any negative x value you plug in, you're going to get the same y value as if you plug in a positive x value. Now for odd functions, f of negative x is equal to negative f of x. An example of this is going to be x to the third power. If you plug in negative x into this, so if you plug in negative x into x to the third power, you're going to get negative x to the third power, which is just equal to negative x to the third power. Reminder that if you have a negative sign raised to the odd power, your thing is still going to stay negative. For example, -1 to the third power is still going to be equal to -1. But if you have -1 raised to an even power, let's say to the 6th power, it's going to be +1. So it's not, when the exponent's even, this negative sign basically, doesn't exist anymore. But if exponent's odd, the negative sign still exists. And notice how, look, so in this case, f of negative x is equal to negative x to the third power. Now imagine if I took f of x, which is my original function, and I multiplied both sides by -1. What I'm going to get is I'm going to get -1 times f of x, or in this case, negative f of x, right? That's the same thing. Negative f of x is equal to negative x to the third power. Notice how negative f of x, so this is a bad negative sign, but notice how negative f of x is equal to f of negative x, meaning that our function is odd. And on a graph, basically what that looks like on the graph is, imagine if you took any point on the graph and you reflected it about the origin. So recall that reflecting about the origin just means that your x and y value basically changes sign. So imagine if I originally had the point -1, -1. Well, if it's an odd function, then that means there's going to be a point where it's +1, +1. All right, so basically all the double negative values turn into double positive values, right? So basically the things just change their sign, to put it quickly. And if a function doesn't meet any of these criteria, so it's not even nor doesn't meet the odd criteria, then it's neither even nor odd. Now, easy way to see if a function is odd or not is if you have a function where all the exponents are even. If you have a function where all the exponents are even, then it's going to be an even function. If you have a function where all the exponents are odd, it's going to be an odd function. All right. So yeah, and you can try it out for yourself. If you plug in negative x into all of these x's right over here, well, what you notice is that if you have negative x and you're raising it to even power, you're just going to get positive x again. So in fact, putting a negative x right over here actually does nothing to our function. So our function actually, so f of negative x, if you plug negative x in for x, you're still going to get f of x, because if you plug in negative x to even power, you're still going to get x, which is what you started off originally, right? And I recommend trying some of these functions out on Desmos and seeing how they work. And if you plug in f of negative x in for x, you're going to get negative f of x if all the exponents are odd. Because, well, take a look at this function right over here. If I plug in negative x into this function, I'm going to get negative x to the third power plus negative x, which just simplifies to negative x to the third power minus x. Notice how I can factor a -1 out of both terms. So I just get negative times x to the third power plus x. All right. And because you're able to factor out a negative sign from both terms, well, notice how on the inside you have your original function. So if this function right over here was f of x, notice how on the inside you have f of x, but then you have this negative on the outside. So notice how negative f of x, so notice how of negative x, right? Because we originally put in negative x into our function. So this right over here is f of negative x, and this right over here, our simplified result, is also negative f of x, right? So because f of negative x is equal to negative of f of x, then this is an odd function. So because with odd exponents, you're able to factor out a negative sign at the end of the day, after simplifying all of this, this is why when you have odd exponents, this remains true. Now, the regions for odd and even functions, it's actually really easy. So basically, the types of problem they're going to give you is they're basically going to say, okay, let's say if you have this function f of x, and it's an even function. Which one of these functions are also even? And they're going to give you f of x plus 1. They're going to give you f of x minus 2. They're going to give you f of x minus 4. And then they're going to give you f of x plus 3. All right. And, so feel free to pause the video and try this problem out for yourself. But basically, the answer to this problem is answer choice number D. Reminder of what this plus 3 does. So whenever you have a function, let's say if you have f of x is equal to x squared, what the plus 3 does is it just moves it up 3 units. But notice how it's still symmetrical, right? Notice how even if I add 3 to this function, the function is still symmetrical about the y-axis. However, if I did something like f of x minus 4, so basically if I have f of x, imagine if I have a function f of x is equal to x squared, right? Then that means if I have f of x minus 4, everywhere I see an x, I replace it with x minus 4. So I'm going to get x minus 4 squared. And remember what this transformation does. If you have x minus something squared, it's going to move that something, it's going to move it to the right by that unit. So in this case, if I have x minus 4 squared, it's going to move my function 4 units to the right. All right, it's going to move it 4 units to the right. And notice how the function isn't symmetrical anymore. Because you moved it 4 units to the right, it's not symmetrical anymore. And same goes for all of these other answer choices. If I move my function, in this case, 1 unit to the left, it's not going to be symmetrical anymore. So reminder that if you have an even function, moving it up or down still makes it even. But moving it left to right doesn't make it even anymore. So that, I think for the regions, that's kind of all you need to know. So yeah, that's something that you don't really have to worry about. I mean, that's still probably going to be like a point on, Algebra 2 regions. Like they're probably going to have like one problem that's like similar to the one I just discussed. But, you don't really have to worry about it too much, I would say. Okay. So now let's focus on focus and directrix. So what's your definition about a parabola? What's the definition of a parabola? You might be saying, okay, the definition of a parabola is just something that looks like this, where it's like a U-shaped, or it can be an upside down U-shape. But, I mean, although that is true, that's not really the mathy definition for it, quote unquote. The math definition for a parabola, imagine if you draw a parabola. So imagine if I draw a parabola. The definition of a parabola is going to be, it's going to be the set of all points that are equidistant from a point and a line. So basically, this parabola right over here, if I pick any point on it, it's going to have the same distance to the line and this line right over here. So it's going to have equal distance from the point, and it's going to have equal distance to the line. And you can kind of visualize this, right? If I pick a point up here, it's going to have the same distance to this point right over here, and it's going to have the same distance to the line. I know this isn't like I should have put my line higher, but you can kind of see the vision, right? So that's basically kind of the definition of a parabola. Any point you pick on the parabola, it's going to be equally distant from this line and this point. The point is something known as the focus of the parabola. And this right over here, the line, is something known as the directrix of the parabola. All right. Now, what you have to know is basically the formula for a parabola. It's y is equal to 1 over 4p times x minus h to the second power plus k. And where h comma k is the vertex of your parabola, and p represents the distance from your focus, to the parabola. To the vertex. Sorry. Okay. So let's actually do a quick practice problem. So there's also sideways parabolas, but I haven't seen them in a while, so I don't really think you have to worry about it. So, let's just do a quick practice problem. So, equation of a parabola that has its focus on the point 3 comma negative 2, 3 comma negative 2, and the directrix at y is equal to 0 is what? So basically, what this question is asking us is, look, imagine if we have our point, basically our focus, right? This focus right over here. Imagine if it's located at negative 3 comma 2. So it's located at negative 3 comma 2. And our directrix is at y is equal to 0. Y is equal to 0. And we want to find out the equation for parabola. Now, what you need to know is that the focus is basically directly above the vertex for my parabola, meaning that it has the same x value. Okay, so the focus and basically the vertex for our parabola is going to have the same x value, but it's going to have different y values. All right, so whatever my parabola is, and also another key thing to note is that you can think about a focus and directrix. So you can think about this parabola. You can basically think about this parabola as basically swallowing the vertex. So swallowing the focus. So the focus will always be inside the parabola, and the directrix will be blocking. You can think about it as the directrix is blocking this parabola. All right. So imagine if I have a function where, I don't know, my focus is here and my directrix is up here. Well, your parabola is always going to swallow. It's always going to swallow the focus. All right. The focus is always going to be inside the parabola, and the parabola is always going to be facing the opposite direction from the directrix. Okay. So in this case, my parabola is going to look something like this, because, right, you notice how it swallows the focus, and it's basically the definition of a parabola is that, it's the set of all points where if you pick any point out on the parabola, it's going to have the same distance from this focus, and it's going to have the same distance to the line y is equal to 0. So the thing about my vertex of the parabola is, remember, it's going to have, the vertex is going to be at the same x value as your focus. But how do you find out the y value for the vertex? And to find the y value, you just take the average between the y values for the directrix and in this case, our focus. So what's the average of 2 and 0? That's going to be equal to 1. And this makes sense because think about it, right? The distance from 1 to 2 is 1. And the distance from 1 to 0 is also 1. So notice how the vertex is equidistant from the point and from the directrix. So I know that my vertex is at negative 3 comma 1. And I know that the distance from my vertex to my focus is 1, right? So my distance from the vertex to this focus is also 1. And this is what I'm going to call p. Okay, so my p value, or this distance, is going to be equal to 1. Now I could just plug it into my formula. So it's going to be y is equal to 1 over 4 times p. I know p is 1, so 4 times 1. It's going to be times x minus h, where h is the vertex, the x coordinate of my vertex. So notice how I have x minus negative 3, right? Because it's x minus h. If I know h is negative 3, it's going to be x minus negative 3, right? Or just x plus 3 squared. And it's going to be plus k, where k is the y value of my vertex. So it's going to be plus 1. So which answer choice meets the criteria? Well, it's going to be answer choice number 1. All right. They're always going to give you an answer choice where it's basically the same thing as the correct answer choice, except that it's going to have the opposite sign on the inside. They want you to mess up on this x minus h part. All right. So always keep that in mind. It's x minus, and then you have your x coordinate. All right. If it helps you, what kind of helps me sometimes is I like to put a parentheses around the h to highlight, maybe I can substitute this negative 3 in, and then you can clearly notice that you have 2 negatives, which make a positive. Also notice that the formula for a parabola is very similar to the vertex form of a parabola. Y is equal to x minus h squared plus k. So if you remember the vertex form for a parabola, all you have to memorize is 1 over 4p, and then you got it. Okay?